Today we want to consider finding antiderivatives, and we want to lead with our basic maneuver, the integral of a power of x. The integral of x to the n dx is x to the n plus 1 divided by n plus 1. So the process is we add 1 to the exponent, and then we divide by the new exponent. What we want to observe is that this is only for n that is not equal to -1. If we try to do this process for n equal to -1, then we end up with 1 divided by 0. And so this could not work when n is equal to -1. But since we know the derivative of the natural log of x is 1 over x, we can turn this derivative statement into an integral statement and say that the integral of 1 over x dx is the natural log of the absolute value of x plus c. A new thing has been introduced here, because I didn't just say the natural log of x, I said the natural log of the absolute value of x. If we start with 1 over x, this has a domain of everything that's not 0. So the only excluded value for 1 over x is x not equal to 0. But natural log does not have the same domain. So that's why we need absolute values around the absolute value. That's why we need absolute values around the x. So that's the first place we will need to think about it. We can think about it. So the absolute values are to match the domain of 1 over x. So the domain here is that x is not equal to 0. And so the absolute values to match the domains. It wasn't a concern when we had the derivative of natural log of x, because we were starting with the natural log of x, where the domain is x strictly greater than 0. And so the derivative is going to be 1 over x, and we're only worried about where x is greater than 0. So the domain here is not more restrictive than the domain we started with. The domain of 1 over x is not more restricted than the domain of natural log of x, so we didn't really worry about anything there. Although the derivative of the natural log of absolute value of x is also equal to 1 over x. So the integral of 1 over x is the natural log of the absolute value of x plus c. The plus c is always going to be present in our indefinite integrals because we don't know, we've lost a piece of information about the antiderivative when we do the derivative process. So this covers all of our powers of x. Also, one that I didn't specifically point out yesterday is that the integral of k dx is kx plus c for k constant. Any questions? Beyond this, we just need our other functions that we're familiar with. So the integral of e to the k, let's just start with x. The integral of e to the x dx is just e to the x plus c. The integral of cosine x dx is sine x plus c. So note that the integral of cosine is sine. The derivative of sine is cosine, so the integral of cosine is sine. That's why there's no negative on the sign. We're not doing derivatives, we're doing antiderivatives. And so it's reverse. The integral of sine of x is where the negative shows up. The derivative of cosine is negative sine, so the derivative of negative cosine is positive sine. So we're going the other direction. We're doing an antiderivative, not a derivative. Any questions? So I want to add to this list here, I want to modify these recent three because these recent three are very, or these last three are very restrictive, too restrictive. Here's something that we know. We know that the derivative of, let's say, e to the 5x, we have to, in the derivative of e to the 5x, we have to use the chain rule. The derivative of e to the 5x is e to the 5x times 5. We also know that the chain rule applies if we have the derivative, let's say, of cosine of 5x. The derivative of cosine of 5x is the sine of 5x, minus sine of 5x, times the derivative of the inside, which is 5. So we get a 5 out in front. The derivative of sine of 5x, once again, we have to use the chain rule. The derivative of sine of something is cosine of that thing times the derivative of the thing. So when we take derivatives of, say, sine of 5x, we get 5 cosine of 5x. What this means is if we turn this around into an integral, if we turn this statement around into the integral statement, we would say that the integral of 5 cosine of 5x dx is sine of 5x plus c. And if we don't have this 5 as a multiple to be the derivative of the inside, then that means we should divide by 5. I can divide this, both sides of this equation by 5. So I could rewrite this as the derivative of 1/5 sine of 5x is cosine of 5x. And so that tells us that the integral of cosine of 5x dx will be 1/5 sine 5x plus c. So in this way, we can add to our 3 important indefinite integrals to remember. So this tells us that the integral of e to the kx dx is 1/k e to the kx plus c. The integral of cosine of kx dx is 1/k times the sine of kx plus c, and the integral of sine of kx dx is minus 1/k times the cosine of kx plus c. That's how we can incorporate the chain rule, or more specifically, the anti-chain rule, in some of our basic derivatives. Any questions? So this will be the important version to remember. Integral of e to the kx is 1/k e to the kx plus c. Any questions? So, other thing to remember is that this process is mostly the inverse of the derivative process. Integration. Yikes. is mostly the inverse of differentiation. What that means is that since differentiation is a linear operator, integration is also a linear operator. Differentiation is a linear operator, which means it respects scalar multiplication and it also respects addition. This means that integration is also a linear operator. So integration will also respect scalar multiplication and also respect addition. So what do I mean by respecting scalar multiplication and respecting addition? This just means we can go a term at a time and we can just carry on our scalar multiples. So for example, if I want the derivative of x to the third, it's 3x squared, following our rules of derivatives. If I want the derivative, if I throw in a scalar multiple, the derivative of 5x cubed, we still do 3x squared, and we just carry on 5 as a scalar multiple. So we end up with 15x squared. We just keep our constant multiples. I should have said constant instead of scalar, but I'm preloading. I'm seeing into the future when we start talking about vectors versus scalars. This means that if we want to integrate, if we know that the integral of x to the fourth dx is add 1 to the exponents and divide by the new exponent, and then put plus c. If we have a scalar multiple of the x to the fourth, like let's say 7x to the fourth dx, we add 1 to the exponent and divide by the new exponent and put plus c, and the scalar multiple just gets carried along. There's our constant multiple. Integration and differentiation are both linear operators, therefore they respect scalar multiplication. We also have to respect addition. This shows up in differentiation if I ask for the derivative with respect to x of, let's say, x cubed plus 7x squared. I'm going to put a plus 2 in there. We can do this as 3 separate derivatives. We'll take the derivative of x cubed plus 7 times the derivative of x squared plus the derivative of 2. So we get 3x squared plus 14x plus 0. It's dual derivatives. I'm going to write it anyway. The derivative of a bunch of terms is the terms is the derivative of a sum is a sum of the derivatives. And the same is going to be true for integration. If I want to integrate x cubed plus 7x squared plus 2 dx, I can do this a term at a time. I can integrate x cubed dx plus 7 integrals of x squared dx plus the integral of 2 dx, and get 1/4 x to the 4th plus 7/3 x cubed plus 2x plus some constant. We can go a term at a time. We need not worry about constant multiples. We just carry constant multiples along. Any questions? All right. Let's pause the video here and then come back and do some more examples.